Okay, mic is on and the recording is live. Now, before jumping into today's topic, I just want to make a little comment about some things related to the group presentations. I've gotten some questions over emails and in person. Just wanted to comment on that. So, if you notice, our Chemistry in Our World presentations will be held during the last 2 weeks of the semester, starting December 2nd. Today is October 23rd. So you have a little over maybe a month and 2 weeks. I don't know the exact number of days before the presentations are due. Now, of course, as of right now, I haven't made the schedule just yet, so you don't know who's going what day, what week. But if we work with December 2nd as our start date, normally what I tell students is after the third exam, after module exam 3 on Monday, is when you are expected to start actively working together, collaborating, meeting, making your slides, start doing rehearsals and all that stuff. One of the biggest reasons for that is since these presentations are meant to tie into topics we covered in class, we hadn't covered as many topics as we could have for a lot of these topics. After module exam 3, the majority of it, the bulk of it, has been covered. Okay, so after module exam 3, so after Tuesday's exam, it is encouraged and expected that you start meeting with your group mates regularly, trying to work on your slides, trying to do those rehearsals. And as we get closer to the presentation, I will tell you what the day-by-day schedule is, meaning who's presenting what day and well, not specific time, but just what day. This is all to say that, obviously for right now, today's Thursday, we have a dry lab tomorrow. Don't worry too much about the presentation right now. Your focus should be the exam on Tuesday, all right? Now, speaking about the exam on Tuesday, Tuesday's exam, oops, here it is, covers the topics that we covered since module exam 2. That includes molarity, pH versus POH, curves, gas laws, and today's topic. I wanted to give you an idea of what that exam is going to look like. The practice exam, meaning last semester's exam, is already posted to Canvas. Visually speaking, your exam will resemble this exam, meaning half of the exam will be multiple choice questions. There'll be 10 multiple choice questions in total for a total of 20 points. The practice exam goes up to 15. Last year, the exam was a bit long, so I've cut it down to 10 multiple choice questions. Those multiple choice questions will comprise the math heavy topics that we've been focused on: molarity, gases, acids, and bases. That's 20 points of the exam. The other 30 points will be based on today's topic, drawing. Now, today's topic, we have a designed workshop for tomorrow. So today we're going to try to get as much of the content out as possible, get some real practice done with me, such that come tomorrow, you get some one-on-one time attempting it yourself. All I can really say about this topic right now is that it's as broadly called drawing, but half of the exam will be today's topic, and the other half of the exam will be all the other math-heavy topics that we've covered so far. Just like this exam, you can expect 6 drawing questions, 3 on top, 3 on the bottom, and then 10 multiple choice questions. Last exam, I noticed that we ran a little long. That tells me I maybe put too many questions. So I've tried to cut it down for module exam 3 with the time that we have. Do we have any questions about the exam or anything about the presentations? Go to the other side for the handout. Go to the other side for the handout. The handout's on the other chair over there. If you want to walk over, that's fine. Okay. Any questions on the exam, tomorrow's workshop, or the presentation? Fantastic. Let's get into it. Today's topic signals a break from all of the math that we've been doing over the last few weeks. In fact, today's topic will not include the roadmap in any way, shape, or form. Today's topic is known as drawing. Specifically, drawing Lewis structures and VSEPR geometries. Now, to understand, before we get into the actual drawing, let's try to take a second to understand a little bit more about what a Lewis structure is and how exactly that helps us identify the VSEPR geometry. Now, Lewis structures, abbreviated here as LS, Lewis structures, are the first step to identifying a compound's three-dimensional geometry. Lewis structures are the first step we take to identifying a molecule's three-dimensional geometry. This three-dimensional geometry is what we know as VSEPR, V-S-E-P-R. We will define it in just a few moments. Now, the way that Lewis structures do that, again abbreviated as LS, Lewis structures explicitly show the nature and location of all valence electrons. Now, there's a term we haven't seen in a while, valence. If you recall, we covered this way back in Module 1 when we were talking about the periodic table and all that nice stuff. That word valence quite literally means outermost. Recall way back when we talked about the concept of electrons and atoms and orbitals, we likened it to that of a planet, where the center of the planet, the nucleus, has rings orbiting around the planet, and these rings are where the electrons can be found. The outermost ring are where we will find our valence electrons. And how do we know how many valence electrons we have or an atom has? It's based on the atom's group number. Take a copy. So let's remind ourselves of what that looks like. We're going to look at the different groups and how many valence electrons each group has. Group 1, 2, 3 to 12 is that transition metal block. 13, 14, 15, 16, 17, and 18. These are all the groups on the periodic table that we should know and remember. I'm just going to draw some lines so I can clearly have some visual separation between them. Group 1 contributes 1 valence electron. Group 2 contributes 2 valence electrons. Groups 3 to 12, if we recall, those are actually our transition metals. And we know a lot about our transition metals at this point, which is namely, we cannot just look at the periodic table and identify how many valence electrons it has, because it's described as variable. That's actually one of the most defining factors about transition metals. Their information is not a set thing that we can identify. It's an investigation. So we don't know how many valence electrons a transition metal will contribute right off the bat. That's okay, though. Group 13 contributes 3, 14, 4, 15, 5, 16, 6, 17, 7. And of course, group 18 contributes 18. I'm sorry, group 18 contributes 8. Do not forget that group 18 is our very special group. These are our noble gases. This is what we talked about when we described them as royalty. We described them as being the atom that everyone else wants to be like, that everyone wants to have 8 valence electrons. While we're on this topic of valence electrons, let's recall ourselves of one primary factor, one primary thing, which is the octet rule. The octet rule loosely describes how atoms and elements want to resemble noble gases. Via their valence electrons. Since group 18 has 8 valence electrons, this is of course referred to as the octet rule. The only exception to the octet rule is that of hydrogen. Hydrogen actually is okay with 2 electrons. This is in stark contrast to the 8 of the octet rule. The reason why it's okay with 2 is because of helium. Helium is a noble gas and has an atomic number of 2, aka it has 2 electrons in total. It simply does not have 8 at all to begin with. So the octet rule describes the fact that atoms in general want to have 8 valence electrons, with the exception being hydrogen, which is okay with 2 electrons because it will closely resemble helium. Now that we understand a little bit more about what Lewis structures are, the information we need to know heading into it, how does this relate to VSEPR? Well, Lewis structures paved the way for the VSEPR geometry. Now, I've been saying that word VSEPR over and over again, but if you look at how I spell it, it's VSEPR. It isn't quite spelled as I'm pronouncing it. Don't worry too much about that. I think that's just the way we've gotten used to speaking about this topic. It's just easier to call it as if though it's spelled through the traditional VSEPR, VES, but we of course know we're referring to VSEPR. VSEPR stands for valence shell. Whoops. Why do I keep erasing? Valence shell electron pair repulsion. VSEPR is the theory that loosely describes that electrons, when present, want to have their own personal space in a molecule. When thinking about this topic, I like to think of it as literally having roommates, and that is within the same room, 2 beds in a room. Each roommate wants their own space. In an ideal world, the room is split perfectly in half. Each roommate gets their own equivalent amount of space. But the truth is that that rarely happens. Rooms have different sizes, roommates have different amount of items. Sometimes you might find that you only have 1 hanger in the closet, 1 space in the fridge, but your roommate's taking up everything else. That's how I want you to think about these electrons. These electrons are those terrible roommates that say, I want my personal space so badly, I'm willing to inconvenience you. And where does this idea come from? Well, electrons are negatively charged. This whole thing revolves around valence electrons. Those electrons will repel one another. Like repels like. So now I'm going to stop talking about what Lewis structures and VSEPR theory is. And I'd like to just jump right into the process. Everyone should have a copy of a handout in front of them. It's about 3 pages long. The very first page is the step-by-step procedure to drawing the Lewis structure of a molecule. You will not be given this procedure as part of the exam. You are expected to learn this procedure, memorize this procedure, and use this procedure when drawing Lewis structures. So what we're going to do right now is we're actually going to go through drawing an example of a simple compound, water, and we're going to go through the steps one by one. So we are going to start with water, aka H2O. We all have the handout in front of us, so I'm going to try as best as I can to keep swiping back and forth, but eventually I'll stop. The very first step says, calculate the total number of valence electrons for the molecule. where each element's group number tells us the number of valence electrons. We saw that earlier, where groups tell us the number of valence electrons, where, for example, group 17 contributes 7 valence electrons. With cations, we subtract electrons equal to the charge. For anions, we add electrons. Now, fortunately, as written, this water molecule is neutral. It is neither a cation nor an anion. So we don't need to worry too much about B in this case. So to calculate the total number of valence electrons, we just look at each element's valence electrons. There are 2 hydrogens and 1 oxygen atom. That's an O as in oxygen. Remember, for my zeros, I like to put a line through it. Hydrogen in group 1 contributes 1 valence electron. There are 2, so 2 times 1. Oxygen is in group 16, hence contributes 6 valence electrons. This gives us a total of 8 valence electrons, here just written as 8 VE. Now, our Lewis structure explains, or by the time that we finish drawing the Lewis structure, all 8 of these valence electrons must be accounted for. The Lewis structure must show the nature and location of all 8 valence electrons. Next step, assume a central atom and arrange other atoms around it. Now, that word is important. It says assume. The fact of the matter is, when you make an assumption, there is a chance you may be wrong. So, inherently speaking, whenever we work through this process, we have to consider the fact that there is a chance we assumed wrong. Now, unfortunately, there is no single 100% foolproof method to identifying what is a central atom. It genuinely is an educated guess. How does that apply to something like H2O? Well, we know there are 3 atoms in total, 2 hydrogens and 1 oxygen. Let's kind of vary it up. Let's switch it up. We could have it such that we have 2 hydrogens and an oxygen. In this case, that right there is our central atom. We could have it in the opposite order, where the oxygen goes first, where yet again, the hydrogen is the central atom. Or we can put both hydrogens on either side, putting oxygen in the middle. Of the 3, one of them should pop out to you as like, that looks correct. Because remember, you are genuinely making an assumption. You're taking an educated guess as to which one is the central atom. Hopefully, we all come to the same conclusion. This bottom one looks the most correct because in truth, what's the difference between these 2 up top? The fact that we can't pick between the ones on top, that ambiguity is what tells us it is not these on top. So, making a comfortable assumption, we put oxygen in the middle and hydrogens on the outside. I have written it in this sort of landscape view from left to right. In truth, it doesn't matter. You could have written it like this, HOH, where just vertically. Or you also could have written it diagonally. All of these are correct because the oxygen is very clearly the central atom. Connect each outside atom to the central atom with single bonds. Okay, so we're connecting the hydrogen to the oxygen, and again, the other hydrogen to the same oxygen. In doing so, by drawing these single bonds, we've actually now added some electrons to this molecule. Don't forget that a single bond has 2 electrons. This is something way back when in module 1. A single bond has 2 electrons, a double bond has 4, and a triple bond has 6. So far, by simply drawing these bonds to connect the atoms, we have actually explained 4 valence electrons. We see where 4 of them are. We can clearly see that there are 2 electrons in each bond. So we know the nature, bonded electrons, and we know their location. That's 4. We still have 4 left. We are then going to distribute electrons working from the outside in. We're going to allocate the remaining valence electrons to satisfy each atom, each outside atom's octet, where this is either 2 or 8 electrons. Looking at the outside atoms first, we have hydrogen. This hydrogen has access to 2 electrons. So this hydrogen is actually happy already. It already has its satisfied octet. The hydrogen on the right currently has 2 electrons. Yet again, the hydrogen is happy. Assign any leftover electrons to the central atom as lone pairs. So those 4 that we had left over will be given to the oxygen in the center, and we'll be pairing them up for a total of 4 oxygen and 2 pairs. Now, I want to be clear on something. This is a visual topic. You are going to be graded based on what you draw. So I want to be clear on something. If you drew your electrons like this, that would be incorrect because they're not clearly paired up. Similarly, you can't just put 3 on top, 1 on the bottom, because again, we need them to pair up. Likewise, you cannot just put all 4 together. They need to be split up in pairs, and it needs to be obvious. That can take this form at an angle, or what I just drew, 2 on top, 2 on the bottom. In doing so, we have now explained the remaining 4 electrons. Step 4, yeah.
Remaining valence electrons to satisfy each atom's octet requirement. You only check the hydrogens, not the oxygen.
We're about to. But actually, let me just go ahead and answer that right now. Before I put those electrons on, the oxygen in the middle had access to 1, 2, 3, 4 electrons. Those remaining 4 electrons that we assign, 1, 2, 3, 4, gets added. And now if we check 1, 2, 3, 4, 5, 6, 7, 8. This oxygen now has a full octet. Step 4, we're going to check happiness. Each bond or lone pair must be clearly indicated. Ensure that all atoms have complete octets. So we kind of just did this, but let's do it again for clarity's sake. The hydrogen on the left has access to 2 electrons. The hydrogen on the right has access to 2 electrons, so they're both happy. The oxygen in the center, after getting its last 4 electrons, is now 1, 2, 3, 4, 5, 6, 7, 8 electrons. By all intents and purposes, this is the final answer. We can clearly see where all 8 electrons ended up. Some of them end up as bonds. Some of them ends up as lone pairs. We're not done yet, though. Step 5 only applies if only the central atom lacks a full octet. It says if only the central atom lacks an octet, consider multiple bonds, continue to step 5. That does not apply here, so we're going to skip step 5. Looking at step 6, check happiness again. However, we did say yes to 4A and 4B up here earlier, so we're going to skip step 6. Lastly, we are going to calculate and clearly indicate the formal charge of each atom. The equation to calculate formal charge is given right here. We're going to take this over and calculate the formal charge of every atom we've seen so far. We're going to start with the hydrogen on the left. The formal charge of hydrogen. The equation is given below. Let's go ahead and plug stuff in. The formal charge is equal to the number of valence electrons. We know that hydrogen in group 1 has 1 valence electron, minus the number of lone pairs times 2. We can see in our drawing that the hydrogen has no lone pairs. So 0 times 2. Minus the number of bonds. We see here that this hydrogen has only 1 bond. 1. This effectively is 1 minus 1, aka 0. So the hydrogen has no formal charge. Let's do the hydrogen on the right. I'm going to label them as HL and HR, where HL just means left hydrogen, HR means right hydrogen. Same process. How many valence electrons? 1. How many lone pairs? 0. How many bonds? 1. So technically speaking, both of the hydrogens have the exact same formal charge. We could have identified that because technically speaking, or at least visually, these hydrogens are identical. They're identical visually in every way, shape, and form. So while we did not need to calculate the second one, it's beneficial to do so just to prove it to ourselves. Lastly, let's calculate the formal charge of the oxygen. How many valence electrons does it have? It's in group 16, so it has 6 valence electrons. How many lone pairs does it have? It has 2 lone pairs. And this is why it's important to pair them up. Because if you misread this and thought it said number of electrons, then you would just say 4 times 2, and that would go wrong no matter what. So we say number of lone pairs, which there are 2, times 2, minus the number of bonds. This oxygen has 2 bonds in total, so minus 2. This is 6 minus 4 minus 2. This is pretty simple math. 6 minus 4 is 2. 2 minus 2 is 0. So this molecule, as drawn, is the correct Lewis structure. And none of the atoms have a formal charge. And that's how you follow the procedure for a single molecule. Yes?
Had a formal structure, would you have to form thing? Have to add it to the answer.
You would, and that's an example we're going to do after this one. Now, we're not technically done yet, because like we said, the Lewis structure is the first step to identifying the compound's 3-dimensional geometry. So we have the Lewis structure. What we want right now is the VSEPR geometry. To identify the VSEPR geometry, we are going to look at the Lewis structure and identify 2 things. How many atoms is the central atom bonded to? And how many lone pairs does that central atom have? Everything revolves around the central atom, oxygen. We see that the oxygen, the central atom, is connected to 2 atoms we see that same central atom has 2 lone pairs. I would now like for us to turn to the last page of the handout, which looks like this. This is what's known as a VSEPR chart. The VSEPR chart provides us with generic templates of various molecules and their sizes and allows us to make a prediction about the shape and geometry of that molecule. As we go through the list, again, remember these are meant to be generic, so they're just generic letters, E and X. What we are going to do is we are going to look for a generic template that has 2 atoms attached to the central and 2 lone pairs. Looking at this one first arbitrarily. It's a bit slow. Let me just wait for it to catch up. Although this central atom does have 2 atoms attached to it, notice that it has no lone pairs. So it would not be this one. I look down here and I see, okay, well, that's a lone pair. Let me count this one. This central atom is connected to 2 atoms, but it only has 1 lone pair, so not correct either. This one down here looks about right. But wait, according to this template, this has 3 atoms attached, which is immediately wrong, and only 1 lone pair. But if we look slightly over to the right, we see a template where the central atom is connected to 2 atoms and has 2 lone pairs. That analysis is what tells us this is the generic template we're expected to follow. So that Lewis structure of water, will most closely resemble this VSEPR geometry. Remember that the VSEPR geometry is generic, so now we need to draw it to match the template. We know our central atom is oxygen. We can see that those hydrogen atoms are bent. And we see that the lone pairs are on these weird-looking bonds. Lastly, we notice the bond angle between the atoms is less than 109. And of course, the generic template gives us the name. This is described as bent, or you can use the word angular. I think bent is the more popular one, though. Now, I'd like to talk about a few facets of this drawing to help us understand what's going on. One of the first things I want you to notice is that I didn't just put 1 less than sign, I put 2. The more less than signs just means very, very less than. For example, if I just wrote less than 109, that could be like 107 degrees. But if I wrote very, very less than, that could be something like 102 degrees. If I kept going, less than 109, that can go to something like 95 degrees. The idea is that it just represents how far away it is from 109. Now, this VSEPR chart that we just used is our guiding principles to predicting geometries. It isn't perfect, but it gives us a starting point. We're able to say that the VSEPR geometry of water is predicted to be bent at an angle of 109, very much less than 109. And the actual data reflects this. Experiments have proven to us that the actual angle of water is 104.5 degrees. Now, I'd like to talk about something specifically about the transition. You're going to look at both me and the board. I want you to pretend my chest is the oxygen, it's a central atom, and my hands are the hydrogens. Now, in the Lewis structure, the way how I've drawn it is that the hydrogens are linear and in line with the oxygen atom with my chest. But what did I talk about when I said electrons are terrible roommates? They want their own space. So the electrons on top are like, I don't want you guys up here. I'm going to push you down. So instead of being at 180 degrees away from each other, they're 104. There are two lone pairs on that oxygen, terrible roommates that are saying, I don't care about you and your bonds. I want my personal space. I'm going to shove you to hell. And that's why VSEPR geometries are so useful to us. They allow us in some way, shape, and form to at least qualitatively predict how terrible those electrons are at sharing. They're willing to push other atoms out of the way. Yeah. We're about to talk about that. Actually, I can talk about it right now since I'm up here. Now, he just asked, and I was going to come to that, those weird-looking bonds on top of that are connected to the lone pairs. There's one that looks like a wedge, and there's one that looks like a dash. The straight lines tell us that those atoms, the hydrogens, are in line with the oxygen atom. They're planar. Those weird-looking bonds are either coming out at you. Whoops, I guess my iPad timed out. Now that I have it on that, let me go ahead and just remember to immediately turn off the auto lock. Where is it? Is it under display? Auto lock? Never. Okay. I didn't share my screen. Jesus Christ. Okay. Okay. Great. So those lone pairs are not in line with the page. In fact, one of them is coming out and one of them is behind me. So I want you to pretend it's like I have an arrow through my chest. I have hydrogens that are in line, they're bent, and I have an electron pair in the front and I have an electron pair in the back. The dashed line means behind, and the wedge means in front. You are not responsible for understanding the intricacies of wedge and dash. That's an organic chemistry topic. All you need to know to do is match the template, because the VSEPR chart tells us everything. The VSEPR chart is supposed to be the easiest part of this process. All we had to do was just match it to the geometry. And the VSEPR chart tells us everything else. Let's do another one. Let's do H3O plus. You all have the handout with the procedure. I'm not going to swipe back and forth. We're going to go one by one. Very first step says, calculate the number of valence electrons. There are 3 hydrogens and 1 oxygen. Each hydrogen contributes 3 electrons, and the hydrogen contributes 6 for a total of 9. But notice that we have here a positive charge. That is what tells us that the overall molecule is a cation. And for this, I'll actually swipe back. For cations, subtract electrons equal to the charge. So the fact that we have a positive 1 plus 1 tells us we will be losing 1 electron for a total of 8 valence electrons. We're now going to draw this structure in full, the Lewis structure following the steps. Remember, by the end, all 8 valence electrons must be accounted for. First things first, we're going to assume the central atom. It makes the most sense that oxygen is a central atom and is surrounded by hydrogens. The way how I have chosen to draw this is I've chosen to put the hydrogen on top. Remember that when we're drawing, we're taking our best guess. You could have put this one on the bottom, and it would have been just as correct. There is just a central atom with other atoms around it. We're then going to connect each outside atom to the central atom. Each single bond has 2 electrons. So by drawing these bonds, we've actually explained 6 of them away. We're left with 2. Now we're going to distribute electrons with the intention of getting to that octet. This hydrogen right here has access to 2 electrons. That is a satisfied octet. Do I need to purposefully spend time evaluating the others? No, they're visually identical. I can make the very confident assumption that they're all the same. So all of these hydrogens are happy. You can prove it to yourself, however. This hydrogen over here on the right has 2 electrons. This hydrogen down here has 2 electrons. So all of the outside atoms are happy. The central atom, as written, has 1, 2, 3, 4, 5, 6 electrons. So as of right now, this oxygen does not have a full octet. Those remaining 2 electrons are going to go to the oxygen. With that, we have explained all 8 electrons. All atoms are happy, including the central atom. So now we're just going to jump straight into the formal charge. I'll get the equation back out, so that way we can refer to it. The formal charge of the hydrogen on the left, we know that it has 1 valence electron. We see that it has 0 lone pairs. And we see that it has 1 bond. This is a total of 0. Do I need to manually calculate the formal charges of the other hydrogens? No. We already talked about them being identical to this one over here. So by calculating 1, we calculated them all. We don't need to waste our time. They're all neutral. Lastly, we have the formal charge of the oxygen. The oxygen has 6 valence electrons. We see that it has 1 lone pair. And in total, 3 bonds attached to it. This is 6 minus 2 minus 3. This is positive 1. And guess what we're going to do? We're going to place that positive charge right on the oxygen atom. I see a hand, yeah. Do you mean if I put it over here or down here, right, for example? It does not matter as long as it's very clearly belonging to the oxygen. So for example, Raphael, if you drew this, that would be wrong because that looks like you're saying that the hydrogen is positive. Right? Just make it clear that you're trying to refer to the oxygen. I like putting in that top right corner because it's very clearly, it's just more clear to me. And here is why we calculate the formal charge. You see, in the previous example, the formal charge was 0. That wasn't very useful to us. that makes sense. Of course, the molecule is neutral. But here, the molecule we're told is positively charged. What the formal charge calculation does is that it tells you exactly, hey, by the way, that positive charge, it's actually on the oxygen specifically. And that's why we calculate formal charge. It tells us which atom specifically holds the charge. Now that we have the Lewis structure, we're now going to identify the VSEPR geometry. We look at the central atom, and we see that this has 3 atoms attached and 1 lone pair. The central atom has 3 atoms attached and 1 lone pair. So now I want everyone by themselves, don't shout out the answer, take maybe 10 seconds or so, try to match which template this is. We're looking for a central atom with 3 atoms attached and 1 lone pair. Scan the table. Hopefully we all get to the same conclusion. This guy right here, trigonal pyramid. So this is the easy part. I already figured out my Lewis structure. Now I just need to draw the, now I just need to draw the VSEPR geometry by matching it. All of the guesswork is taken out for me. I can clearly see, according to the template, what's on a wedge, what's on a dash. So we're going to draw it. We have oxygen in the center, hydrogen on a wedge, hydrogen on a dash, and then on top, we have our lone pair. The angle between the atoms is less than 109 degrees. Recognize that this is just one less than symbol. And we can see the name of the geometry is trigonal pyramid. All that's left, of course, I see your hand, I'll get to you in a second. All that's left, of course, is to remember to place the positive charge. Because, of course, the molecule was positive to begin with. We already figured out where the positive was. We have to remember to keep it. I saw a hand earlier. Yeah, what was your question? Very good question. You do not need to memorize this chart. It will be provided to you as part of the exam. However, you will need to memorize the procedure. And this has happened before with stoichiometry, with reactions. You have to follow the steps in order. So you will be given the VSEPR chart as part of the exam. Recognize, of course, that the trickiest part is identifying the Lewis structure. Before we move on, does anyone have any questions on H3O+? Okay. Let's try another one. One you might recognize, one you should recognize. NO3-. This is that polyatomic ion. One thing we immediately notice is that there is a negative charge. As of right now, we don't know which atom the negative charge belongs to. Just like over here, we didn't know that the positive was going to be on the oxygen. But we know by the end, we will figure it out. So follow our steps in order. We're going to count valence electrons. There is 1 nitrogen. There are 3 oxygens. Nitrogen is in group 15, so 5. There are 3 oxygens, each of which contributes 6. And don't forget, in the case of anions, we add an electron. Remember when we did the cation, we subtracted. When we have the anion, we add. This gives us a total of 5 plus 18 plus 1 for a total of 24 valence electrons. A lot more than we're used to dealing with, but we're going to trust the process. First things first is we're going to assume a central atom. Does anyone want to take a guess what we can say the central atom is? Nitrogen. It makes the most sense that there is a nitrogen in the middle with 3 oxygens around it. That just makes the most sense. And remember, that's all this assumption is. It's an educated guess. I always get students asking, can we use this logic? And I'm like, that logic works 90% of the time. What if on the exam I give you a 10% opportunity? Next, we're going to connect each outside atom to the central with single bonds. In doing so, we have explained away 1, 2, 3, 4, 5, 6 electrons. Left with 18. Now we're going to check how we're going to distribute electrons working from the outside such that they satisfy their full octet. Starting with this oxygen on top, we see that it has 2 electrons. Now you may be thinking, well, 2 electrons is helium, right? So that should be fine. Look at the periodic table on the wall. Which halogen, which noble gas is oxygen closest to? Neon. So it's actually looking for that 8. So guess what we're going to do? We're going to put 1, 2, 3, 4, 5, 6 electrons on the oxygen, lone pairs. So 1, 2, 3 lone pairs. And now this oxygen has in total 8 electrons. We can apply that exact same logic to all of the other oxygens, where to satisfy their full octet, 3 lone pairs will be put on them. And if you're keeping track of the math, 2, 4, 6, 8, 10, 12, 14, 16, 18, we have now explained the remaining 18 electrons. Now we're going to check happiness. We've already checked the oxygens, so all of the oxygens are happy. But looking at the nitrogen, we see 1, 2, 3, 4, 5, 6 electrons. This nitrogen, as written, is unhappy. So let's go back to our steps. What does the step say? It says, if only the central atom lacks a full octet, consider the possibility of multiple bonds. Continue to step 5. Step 5 reads, convert the lone pairs on outside atoms to bonds to the central atom. What the hell does that mean? So the nitrogen right here has 6 valence electrons. It only needs 2 more. So going back to our roommate analogy, this nitrogen says, hey man, I'm kind of running low on electrons. Do you mind just lending me some electrons this time, just so I can get to the 8? Notice I've picked the oxygen on the right. Does it matter which one we ask? No, they're all identical. So I'm going to arbitrarily pick the one on top, and I'm going to convert that lone pair into a bond. Remember that 2 electrons make a bond. This is what leads to a double bond on the nitrogen. Now, it's very important to recognize something. The electrons that were on that oxygen, they haven't been stripped. They haven't been kicked out. They've simply been converted. Because that oxygen on top still has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. So we're not removing the lone pair, we're simply converting it. In doing so, the nitrogen now has 1, 2, 3, 4, 5, 6, 7, 8. Every atom is now happy with its full octet. All 24 electrons have been accounted for, and the molecule, by all intents and purposes, is happy. All that's left is to calculate the formal charge. Starting with the oxygen on the left, 6 valence electrons, 3 lone pairs, and 1 bond. This is equal to -1 overall. Sorry, -1 overall. The formal charge of the oxygen on the right, I can immediately say is also -1. Why? Because both of these oxygens are identical to one another. So now I just need to put that negative charge. Can I make that same assumption for the oxygen on top? No. Remember, this is a drawing topic. It's very visual. Visually speaking, this oxygen on top is not identical to the others. So we have to manually calculate it. Oxygen has 6 valence electrons. It has 2 lone pairs. And we see that it has 2 bonds. This is 6 minus 4 minus 2, which is a whopping 0. Lastly, we will now calculate the formal charge of the nitrogen. Nitrogen has 5 valence electrons. It has 0 lone pairs. And it currently has 4 bonds in total. This adds up to +1. We're then going to put that positive charge on the nitrogen. And now, looking at the final structure, does this explain where the negative comes from? Yeah. The positive and the negative will cancel each other out. And all you're left with is a single negative charge. And here again is the beauty of the formal charge calculation. In the previous case, the molecule was overall positive, and we found out only one atom had a positive charge. But sometimes, like NO3, there are cases where multiple atoms have a charge, but the sum of those charges is -1. Do we have any questions on NO3- so far? Remember, this is the bottleneck. This should be the slowest/hardest part. Guess what we're going to do now? Now we're going to figure out the VSEPR geometry. Redrawing the molecule really quickly. We want to take a look at the central atom, we can see that the central atom is attached to 3 atoms and 0 lone pairs, here abbreviated as LP. So look at your VSEPR chart. Try to identify which template we will be using that has 3 atoms and no lone pairs. Remember, you will be given this chart, so it's more important to me that you know how to read this chart than memorize it. Hopefully, we all came to the same conclusion. Trigonal planar. So we're just going to take this template that we identified and we're going to try our best to match it. We have a nitrogen in the center. We have our oxygen on top, our other oxygens at some odd angle. We know the lone pairs are on the atoms. We can see from the geometry, the bond angle is 120 degrees. And the name of the geometry is trigonal planar. Now I'd like to talk about something specifically. Number 1, notice that we had a double bond in our Lewis structure. Technically speaking, none of the templates have a double bond in it. That's because they're just templates. They're meant to be generic. So the fact that we have a double bond here should not affect what the VSEPR geometry is. That's why we only look at number of atoms and number of lone pairs. Secondly, remember how I talked about those electrons being terrible roommates? Look at what happens when there are no electrons. This is a perfect 120 split. This is an equilateral triangle by all intents and purposes. Everyone gets their own space because there is no terrible roommate saying, I'm going to force you to get uncomfortable. Do we have any questions on NO3 minus? Okay. Let's try another one. Let's do OH minus. Hydroxide, another polyatomic ion. I don't expect you to have the steps memorized yet, but hopefully we're getting more comfortable with it. First thing is to calculate valence electrons. Oxygen contributes 6, hydrogen contributes 1, and that negative charge contributes another 1. This is a total of 8 valence electrons. Then we're going to pick a central atom. Except we only have 2 atoms. Technically speaking, you can't have a center with only 2 things. So we can just clearly write OH. Neither one is the center. It's only 2 atoms. Doesn't affect our process too much. We're going to connect the 2 together. And in doing so, we've explained 2 electrons. Now, we're going to look at each atom and satisfy their octet. From the perspective of the hydrogen, it has access to 2 electrons. It is currently happy. From the perspective of the oxygen, it currently has access to 2 electrons, which is not ideal. So we're going to place those remaining 6 on the oxygen. In doing so, we've explained all 8 electrons, and both atoms are happy. We're now going to calculate formal charge. Formula is down here. The formal charge of oxygen, it has 6 valence electrons, 3 lone pairs, and 1 bond. This is a total of -1. Then we want to check on the formal charge of the hydrogen. 1 valence electron, 0 lone pairs, and 1 bond. This is 0, aka neutral. Okay. So we're pretty confident in our Lewis structure. It has all 8 electrons. We've explained the negative charge. Everything looks good. Now we're going to check the VSEPR chart. Do we see a template of just 2 atoms? No. Why is that? Well, simply put, the geometry of 2 atoms will always be linear. So the Lewis structure is also the VSEPR geometry. And recognize there is no angle associated with this. You traditionally need 3 points for there to be an angle. This is only 2 atoms. So the big takeaway here is that whenever we're dealing with just 2 atoms alone, it will always be linear. It is not one that you will see on the VSEPR chart. It's on you to recognize that the shape between 2 points will always be a straight line, aka linear. Yes. Yes. Hydrogen right now has access to 2 electrons, which resembles helium. It's happy. Previously, before putting on those lone pairs, the oxygen also had access to 2 electrons. But remember, oxygen is close to neon on the periodic table. So it wants 8 in total. So we place those remaining 6 on the oxygen. Yeah. Is that Michelle? Yeah. On the central atom, everything comes back to the central atom. There are lone pairs on the outside oxygens, but when looking at VSEPR chart, we're looking specifically at the central atom. In the case of NO3, that central atom had 3 atoms attached and no lone pairs on it. It all comes back to the central atom. Any other questions? All right, in the time that we have left, let's just do one more. Let's do a simple one. CH4. Carbon in group 14 contributes 4 electrons. Hydrogen contributes 1, and there are 4 of them in total, so 4 electrons, for a total of 8. Reasonable to assume that the carbon is in the center and is completely surrounded by the hydrogens. We're then going to connect each outside atom to the central with single bonds. In doing so, we have explained 1, 2, 3, 4, 5, 6, 7, 8 electrons. So there's nothing left to allocate or distribute. We're going to check happiness. From the perspective of this hydrogen, it has access to 2 electrons. That closely resembles helium, so it's happy. Since all of the hydrogens are visually identical, I can easily say all of the other hydrogens are happy. You can prove it to yourself. And then looking at the central atom, carbon, it has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. So in fact, everything here is happy. This molecule is done. No lone pairs, no double bonds. That's it. All that's left is to calculate the formal charge. I'll get the formula back up. Starting with the carbon first. Carbon has 4 valence electrons, 0 lone pairs, and 4 bonds in total for a whopping 0 overall. The formal charge of the hydrogen, it has 1 valence electron, 0 lone pairs, and 1 bond for a whopping neutral. Do I need to spend time to calculate the other hydrogens? No. They're all visually the same. This right here is our Lewis structure overall. To get the VSEPR, the central atom has 4 atoms attached, 0 lone pairs, written here as LP. Take a quick scan for yourself. Try to identify it. I see a hand in the front. What's up? Yes, you always have to check for the formal charge. As seen in this example right here, NO3 minus, there are cases where overall it will add up to a different charge, but individual atoms may have their own charge. That's a good question. You always have to calculate formal charge. In fact, I can promise you on the exam, the instructions will say, be sure to label any formal charges, if any. If it's neutral, you can leave it blank, like up here. So you will be needing to calculate formal charge. So look at our VSEPR chart. We're looking for a central atom with 4 atoms attached, no lone pairs. We should all reach to the same conclusion, tetrahedral. Remember that the VSEPR chart part should not be the difficult part. That's just matching. That's a visual cue. The hard part is drawing the Lewis structure. So we have the template. Now we're just going to draw it out. We have carbon in the middle. We have hydrogens on some bonds. And then hydrogens on the wedge and the dash. The bond angle is 109 degrees. And it is labeled tetrahedral. As a reminder, you are not responsible for understanding too much about this wedge and dash. This is an organic chemistry topic. All you really need to know is that the dash is in the back and the wedge is in the front. That's really all you need to know. I see a question right here. What's up?
For example, like NaCl, that would be linear.
NaCl, 2 atoms, linear. Correct. We have a dry lab tomorrow, a workshop on this topic. I'll come with worksheets prepared. The only other thing I want to mention before I let you go is look at your handout at the footer. You will never be asked to provide the geometry of a molecule with a transition metal. Transition metals do not exist in this topic because of that variability. We're going to end lecture for today. If you have any questions, come talk to me right now. If not, I'll see everyone tomorrow at lab.